In section 9.2, we are going to be looking at continuity. When you think about natural phenomena, they generally have continuous graphs. But when you are talking about business and economic applications, they frequently have discontinuities. One perfect example of a discontinuous function is postage. If your mail weighs less than 1 ounce, you pay one price. If it pays from 1 ounce to 2 ounces, you jump up to a different price. The prices don't go up continuously, they jump from one to another. That's a discontinuity. In order for a function to be continuous at some x value of c, all three of the conditions that we are going to look at must be met. Condition 1, f of c exists. This means that the function does have a y value at the x value of c. Condition 2 is that the limit as x approaches the x value of c for the function f of x must exist. Condition 3 is that the limit as x approaches c of the function f of x must be equal to f of c, or the y value at exactly c. It is important to know that every polynomial function is continuous for all real numbers. You don't have to consider it. If it's a polynomial function, then it is continuous. Every rational function is continuous at all real numbers except those numbers that make the denominator equal 0. In our first example for continuity, we are asked to find any points of discontinuity in the given graphs, and for each that we find, we want to state the condition of continuity that we did not meet. When you are looking at a graph, one of the basic things to think about is, do I have to pick up my pencil if I want to trace this graph? So in looking at our graph, starting at the beginning here, we can trace okay till we get to 1, and then we'd have to go around the circle and pick our pencil up to go up here to get to the dot. So at the x value of 1, we are not continuous. So our next part is to figure out what condition did we not meet. Always go in order. The first condition is, does the function exist? Is there a y value at the x value of 1? So what you're really looking for is there a solid dot somewhere at 1? Well, yes, the solid dot's up here. So the function does exist. Condition 2 says that the limit must exist. As I come at the x value of 1 from the left side, I'm going into the y value of 2. As I come at the x value of 1 from the right side, I am also coming at the y value of 2. So my limit does exist. My limit is 2. Condition 3 says that the value of the function and the value of the limit have to be the same. Well, we said that the value of the function is 3 and the value of the limit is 2. They are not the same. So the condition that is not met is that f of 1 is not equal to the limit as x approaches 1 of our function. So now let's continue tracing our function. We finished at 1, so now we're tracing and we come down to 2, and then we would have to pick our pencil up and do our open circle to begin tracing again. So another place where this function is not continuous is at the x value of 2. Again, go in order. Does the function exist? Is there a solid dot at the x value of 2? Yes, it's down here at 1. So we meet condition 1. Condition 2 is, does the limit exist? As I approach 2 from the left side, I am going into the y value of 1. As I approach 2 from the right side, I'm going into the y value of 2. I'm going into 2 different y values, so my limit does not exist. So that's the condition that we did not meet. The limit as x approaches 2 for this function does not exist. So now we know that we are not continuous at 2. If we continue tracing this thing, we would get up here to 3, have to pick up our pencil to make the open circle, and then continue to the end of the function. So the next place where we are not continuous is 3. Rule 1 says that the function must exist at that x value. Does the function exist? Is there a solid dot anywhere at the x value of 3? No, there's not. So that's the condition we broke. So what we would say is that f of 3 does not exist. On the second picture, from the beginning of the function, we would start tracing and we'd get closer and closer to this asymptote, and then we would have to pick our pencil up before we could start tracing again. So we can say that at the x value of 1, we are not continuous. Going in order, condition 1, does the function exist at 1? No, it does not, because 1 is an asymptote. So the condition that we did not meet is that f of 1 does not exist. Now, if we continue tracing on our graph, we'd come here to where x equals 2, and we would have to pick up our pencil to begin again. So 2 is the second place where we are not continuous. At 2, question 1, does the function exist? Do we have a solid dot? Yes. So that condition's okay. Question 2, does the limit exist? From the left side of the x value 2, you're going to the y value of 1. From the right side, you're going to the y value of 2. 2 different y values means the limit does not exist. So the condition that we broke is that the limit as x approaches 2 of this function does not exist. Then, as we would continue tracing this thing, we would come to this open circle where we'd have to pick up our pencil before we could continue on. So 3 is also a value where we are not continuous. Condition 1, does the function exist? Is there a solid dot at 3? No. So our rule that we broke is that f of 3 does not exist. In example 2, we are asked to determine whether the function that we are given is continuous. If it is not continuous, we need to identify where it is discontinuous and which of the conditions fails to hold. On the first example A, we are given the function f of x equals 3x plus 5 over 2x minus 7. This is a rational function. We were told in one of the starred statements earlier that rational functions are continuous everywhere except where the denominator equals 0. So let's find where the denominator equals 0. Set your denominator equal to 0, and you get x equals 7/2. When x equals 7/2, the denominator is 0, which means the function does not exist. So this is not continuous at x equals 7/2 because f of 7/2 does not exist. On example B, we are given the function 3x squared minus 5x plus 3, which is a polynomial function. Our first starred statement told us that polynomial functions are continuous everywhere. So for this one, you would just say that it is continuous. On example C, we are given another rational function. Rational functions are not continuous where the bottom equals 0. So we need to set that denominator equal to 0. When you set a squared equal to 0, you want to try to factor that thing. This does factor. This factors into x minus 8 times x plus 3. So the places where this function has a denominator equal to 0 are at 8 and negative 3. This means the function does not exist at those values, so we would say that we are not continuous at x equals 8 because f of 8 does not exist, and at x equals negative 3 because f of negative 3 does not exist. On example D, we have a piecewise function given to us as the function we are going to investigate its continuity. The first row is a quadratic polynomial. The second row is a linear polynomial. Polynomials are continuous everywhere. We are switching from the quadratic to the linear at the x value of 4. So the only place where this might not be continuous is at that x value of 4. So what we have to do is check our 3 rules for continuity and see if they are met or not. Rule 1 says, does f of 4 exist? That's the first thing you have to check. Does the function exist at the value that you are checking? In order to see if it exists or not, you just need to see, do you have an equal to somewhere? Yes, on the bottom row, we have the greater than or equal to, so does the function exist at 4? Yes. For rule 2, you want to know, does the limit as x approaches 4 of this function exist? Remember when we did limits in section 1 and we had a piecewise function, we had to do the limit from the left and from the right. So we are going to look at the limit as x approaches 4 from the left of this function. If we are looking from the left, then we are looking at the items that are less than, and that is the quadratic piece of the function. But this quadratic is just a polynomial, so we just need to substitute 4 into our polynomial. We will get 16 minus 20 plus 6, and that answer is 2. So the limit from the left equals 2. Now we need to look at the limit from the right as we approach 4. The items on the right are greater than, which is the bottom row of our function, which is the polynomial 4x minus 8. If we put 4 into that, we will get 16 minus 8, which equals 8. So the limit from the left is 8. The limit from the right was 2. The limit from the left was 8. So that means that our limit does not exist. So the answer to our question is no. If that answer is no, that tells you that the function is not continuous. So we would say that f of x is not continuous at x equals 4 because the limit as x approaches 4 of this function f of x does not exist. On example E, we have a 3-row piecewise function, and this one's a little different. The top row uses the function negative x for x's that are less than 0. It is telling us that y equals 1 if x equals 0. And our third row uses the function of y equals x for x's that are greater than 0. Each of these is still a polynomial function. They are very small, short, easy polynomial functions, but they are still polynomial functions. So they would be continuous, except we're switching from one to the other to the other. And where does that switch happen? It happens at 0. So the x value of 0 is what we need to investigate. For Rule 1, does f of 0 exist? Is there an equal to for the x value of 0? And yes, there is. It's in row 2. So does the function exist? Yes. When we look at that row 2, what that is telling us is that y equals 1 if x equals 0. So you can think of that as two different formats. You could write it as the point of x equals 0, y equals 1, or you could say the value of the function at 0 equals 1. Now let's think about Rule 2, which asks, does the limit as x approaches 0 for this function exist? So we need to do, because it's piecewise from the left and from the right, so the limit as we approach 0 from the left of this function means items that are less than 0. The items that are less than 0 go with the function negative x. And if you put 0 in for x there, you just get 0. Now do the limit as x approaches 0 from the right for this function. If you are looking for the items that are greater than 0, then you are using the bottom row, which is the function x. And if you put 0 into that, you get 0. Did we get the same answer for both limits from the left and the right? Yes, we did. So we now know that the limit as x approaches 0 of this whole function is 0. Question 3 asks us, is f of 0 equal to the limit as x approaches 0 for this function? Well, go up to step 1. The value of our function is 1. In step 2, the limit of our function is 0. They are not the same. So what that tells us is that f of x is not continuous at x equals 0 because f of 0 is not equal to the limit as x approaches 0 of our function.